In this video, what I want to do is I want to give a proof of this corollary of Cauchy's theorem. Of course, I kind of intuitively talked about how this follows from the main theorem, but I'm not going to prove the main theorem. So I still want to prove this corollary because it's got a really nice proof. I think the proof is really pretty. The proof involves Green's theorem from calculus. So let me first remind you of what Green's theorem says. So Green's theorem is the theorem about line integrals. And it says that if you have a line integral, so if you have p of xy dx plus q of xy dy, and you evaluate this over some integral, over some path gamma, then this is going to be the double integral over the region determined by, so this is a closed path. There's a really deep theorem in math called the Jordan curve theorem, which is a theorem that sounds totally obvious, and yet it's a super deep theorem and really a pain to prove. So it's one of those reminders that not everything that's obvious in math is easy to prove, and not everything that's easy to prove is obvious, and not everything that's obvious is even true. So you have to be really careful. But anyways, there's this thing called Jordan's curve theorem, or the Jordan curve theorem. So the Jordan curve theorem basically says that if you have any closed simple curve in the plane, something like that, or any closed simple curve, then that's going to subdivide the plane into two pieces. There's an inside and an outside. And here, if you have a curve gamma, since gamma is a closed curve, this is going to completely define a bounded region A. So that's what I'm saying A is. Okay. And so this is, Green's theorem says that if you can compute this line integral, this is the same as the double integral over the region A of the quantity q sub x minus p sub y dx dy, where you're integrating again over this double integral over the region A. And so that's Green's theorem. And just as a reminder, remember that the integral of p dx over gamma is defined as the integral from, let's say gamma has parameterizations from a to b, but this is going to be p of gamma. So let's say gamma of t is x of t, y of t, where t goes from a to b. Then this line integral is going to be the integral of p of gamma. So it's p of x comma y times, since it's dx, it'll be x prime of t dt. And then the integral of q of x dy would be very similar, except you'd have a q and then a y prime of t dt. Okay, so Green's theorem gives this kind of equivalence between line integrals and the region determined by this line integral. Okay, so this region A determined by this, the inside of this closed curve. So that's Green's theorem. And what this has to do with us is, remember that we're looking at this integral. We're assuming that f is holomorphic. Okay, so we're assuming that f is holomorphic over this region G, and that gamma is piecewise smooth and homotopically equivalent to a point. Okay, so if that's the case, then the integral of f over this curve is 0. So let's just kind of put all the pieces together and see how this works. Let's assume, let's assume that f can be written in the usual way as u plus iv. And let's write z is x plus iy. The reason for that is that dz is going to be dx plus I dy. And if you calculate the integral of f over gamma, f of z dz, this is going to end up giving you the integral of u plus iv times dx plus I dy. And it turns out that you could distribute these. That's the proper way to do this. And this would be the integral of, let's see, u dx minus v dy plus I times the integral of v dx plus u dy. Okay, and that's the integral over gamma. And so this is going to be, by Green's theorem, the double integral over the region G, where what you're going to do is you're going to take, so remember how Green's theorem worked is that if you take the p dx and q dy. And so this is going to be the partial of q with respect to x minus the partial of p with respect to y. So that means that we're going to take the partial of negative v with respect to x minus the partial of u with respect to y. And that's going to be dx dy, or dx dy, yeah, that's fine. So dx dy plus I times, again, the double integral over g of, let's see, u sub x minus v sub y dx dy. And now remember that we assumed that f was holomorphic. And what does holomorphic mean? Well, it means that it satisfies the Cauchy-Riemann equations. And remember, the Cauchy-Riemann equations tell you that if f is u plus iv, then u sub x is equal to v sub y, and u sub y is equal to minus v sub x. And it turns out that if f is holomorphic and therefore satisfies the Cauchy-Riemann equations, then both of these integrals are 0, and therefore the total integral is 0. Okay, and so there's a nice proof of the corollary of Cauchy's theorem that we were looking for. And again, it used Green's theorem and the Cauchy-Riemann equations.